Alright, so this video will look at some short-run behavior of a few different rational functions. Remember, rational functions are those that can be expressed as a ratio of polynomials. So the top is a polynomial, the bottom is a polynomial, the denominator cannot be 0, but polynomials could be degree 0, degree 1, degree 2, and so on. So there's a few things to help keep in mind when we want to look at that short run behavior, that behavior in the middle, not the long run on the ends, but the short run in the middle, the turns, the asymptotes, the intercepts. So there's a few things to keep in mind to help us try to figure out what the graph will look like, what the function does as a picture for behavior. One thing to look at is y-intercept, and that's really easy. All you're going to have to do is plug 0 in for x and solve for the one y-intercept value. It will not have more than one. It may not have one. The x-intercept is something that we'll look at, and for rational functions, we're going to set the numerator equal to 0, and that's going to tell us where the rational function has any zeros, if it does, and it may not have any, but that's how we can find x-intercept, is just set the top function equal to 0. Vertical asymptotes we've covered before. That's where we'll look where the denominator is 0. It's where it'll make the function undefined, values that aren't included in the domain, that sort of thing. And then the last thing that we'll look at is the horizontal asymptotes that are possible. And that's going to tell you the long run behavior at the ends, and those will be one of three things that will happen where you compare the leading term of the top and the bottom polynomial and see how those degrees compare as to whether or not the end behavior goes off to infinity, tries to approach 0, or tries to approach some other integer value, or even a real number value, not just an integer, but positive or negative, depending on what those coefficients do. So those are 4 areas that we can look at. We'll also look at function behavior around those asymptotes to help figure out whether the function approaches it to infinity or negative infinity. But here are a few examples that we'll look at. All right, so for the first one, we have the function x minus 2 divided by x plus 1 times x minus 3. It's already in factored form. And we can look at, it's in polynomial form, polynomial on the top, polynomial on the bottom. The degree of the bottom will be x squared, but you don't need to multiply that out for right now. So to begin with, we'll look at finding the x-intercept. I'm just going to sort of draw a little graph over here for now for us to play with. X and y. Okay, so x-intercept is where we will set the numerator equal to 0. It's where the function itself equals 0. So in order to do that, we'll take that top x minus 2 only and set that equal to 0. And what that will result in is an x value of 2. So we have an x-intercept at 2, and I can go ahead and plot a point there. All right. Next we'll do y-intercept. And y-intercept is where it's the y value where x is 0. So we can just take our function y equals and plug 0 in for all the x's. 0 minus 2 over 0 plus 1 times 0 minus 3. We get negative 2 on top and negative 3 on the bottom. So our y-intercept is a positive 2/3. So 2/3 would be 2/3 of the way up to 1. Any vertical asymptotes are going to be seen where the denominator equals 0. Since it's already in factored form, x plus 1, x minus 3, then you just set each of those equal to 0. So we have x value at negative 1 and an x value at 3. Those are going to be areas where the function is undefined. They are not in the domain of the function, and at negative 1 and at positive 3, we have a vertical asymptote. So I'll put those on the graph. All right. Horizontal asymptotes are going to sort of tell us what it does in the long run. It looks like we'll have 3 pieces on this, only because the 2 vertical asymptotes sort of separate the middle. Horizontal asymptotes are where we're going to compare the leading term of the top to the bottom. So the top has an x on it. The bottom, if you multiply it out, the highest term will be x squared. So this is a case where the denominator degree is less than the, numerator degree, sorry. The numerator degree is less than the denominator degree. The bottom will grow a whole lot faster, so the function as a whole will end up going to 0. So it has a horizontal asymptote at y equals 0. I'll draw that with a different color so you can see it. So y equals 0 is a horizontal asymptote. So that's graphically what we can pull. The other thing that you can consider is there's some graph pieces, but without actually, creating a little XY chart and plugging in values and functions, it's going to be, you're going to have to try to figure out what the behavior does. So if you'd like to look for, so where does the graph live? So when x goes to both positive and negative infinity, we've determined that the function goes to 0. But the question is, does this left piece live on the bottom or does it live on the top? So we can determine that if you'd like to look at, as x goes to negative infinity, look at values like -2, -3, -4, and so on, and see what the function value, the sign is. If it's negative, it'll live in this lower region, and if it's positive, it'll live in this upper region. So if we look at our function, it's x minus 2 over x plus 1 times x minus 3. If I plug in negative values to the top, -2 minus 2, -3 minus 2, the top's going to be negative. And if I plug those same negative values in the bottom, -2 plus 1, -3 plus 1, that left quantity is going to stay negative, and that right quantity is going to stay negative. And if you do a negative divided by negative times a negative, your end result will end up being negative. So when x tries to go to negative infinity, that portion of the graph will live down here in this lower left region. Okay? We can do the same thing as x goes to positive infinity. We already know that as x goes to positive infinity, the function value goes to 0. But does it live in the lower half or the upper half? So we can look at values bigger than 3 because that's where our asymptote is. So like x equals 4, 5, 6, 7, so on. And if you plug that into the function x minus 2, x plus 1, the top's going to be positive. The x plus 1 portion will be positive, and the x minus 3 portion will be positive, right? 4 minus 3, 5 minus 3, 6 minus 3. Anything above 3 that we plug into the original function, all of those pieces will stay positive. So as x goes to infinity past that asymptote, the function will live in the positive area for function values. All right, now the piece in the middle, it could be a parabola shape where it's concave up or concave down, or it could be an odd powered shape, cubic or whatnot, to where it has sort of like a wiggle in the middle. So if you can look at sort of the sided limits, that'll sort of help with that. So if we look as the function, as the function tries to go to 3, if we look as the function tries to go to this vertical asymptote of 3, it's going to be from the left, correct? Because we're on the left, we want to look at what the function does to the left side of 3. So if we try to look as the function goes to 3 from the left, that's going to include numbers like 2.6, 2.7, 2.8, and so on. And if we look at what those do in this x minus 2, x plus 1, x minus 3, the top, 2.6 minus 2, 2.7 minus 2, the top will be positive. The bottom, 2.6 plus 1, 2.7 plus 1, 2.8, the bottom, the left piece will be positive, but the right piece, the x minus 3, is going to be negative. So in that region, as the x value tries to approach 3 from the left, the function values end up being negative. So that means our graph here is going to point down. And we can do the same thing, get rid of some of this other here. We can do the same thing as x tries to approach -1 from the right. we want to try to figure out as it comes to that that vertical asymptote from the right, what does the graph do? So if we look at -1 from the right, those are values like -0.2, -0.5, -0.8, something trying to approach -1. What happens to the function values? So the top, the x minus 2, that'll be negative. The bottom, the x plus 1, if you do -0.2 plus 1, -0.8 plus 1, anything not -1, and you add 1 to it, you're going to end up with a positive number. And then if you take all those numbers and subtract 3, like -0.2 minus 3, -0.5 minus 3, -0.8 minus 3, then that right quantity will be negative. And you'll have a negative over a negative, which will be positive, so your graph is going to go up. So as it approaches -1 from that side, it'll raise up, and there is your graph. There's a piece over here on the left lower. There's a cubic or odd shaped piece in the middle that has a x-intercept and a y-intercept, and then there's another portion of a curve in the upper right hand corner. And yeah, you can always graph these to verify, but you should be able to look at the long run behavior and see if the function lives in the positive function area or the lower negative function output area, and then you can look at these sided limits to see what the function does around the asymptotes. All right, so there's the graph for this example. Looking at another one, here's one, y equals 2x plus 4 over x minus 1. So for this one, go ahead and get this little graph going so we can sketch as we go. Here's x, here's y. All right, so if I start with x-intercepts, for a rational function, the x-intercepts are anything that make the numerator 0. So if I set the numerator equal to 0, I get that x is -2. So I'll come to -2, plot my x-intercept. All right, y-intercept. Y-intercept is where we're going to set all the x values equal to 0. So if I do that, 2 times 0 plus 4, 0 minus 1, I get 4 over -1, so -4. So at -4, we have a y-intercept. All right. Vertical asymptotes are going to be any value that make the denominator undefined. So if we look at our denominator x minus 1, the only value that's not allowed for this function is going to be an x value of 1. So we'll come to 1. And we'll make us a vertical asymptote. So vertical asymptote at x equals 1. Looking at any horizontal asymptotes, that's going to be where you compare the degree of the numerator to the degree, the highest power on the denominator. This one happens to be 2x on top and x on the bottom, so they're equal because they're both x's are powers of 1. So if you look at 2x over x, and you look at the coefficients, the 2 over 1, you get the value of 2. So what this graph does is it has a horizontal asymptote at y equals 2. So if we come up to 2, make ourselves a horizontal asymptote, then what's going to happen is at the ends of the graph, I don't know if it's going to be above or below, but at the ends, the long run behavior will approach the y value of 2. We just have to figure out where this function lives based on some other information. Okay, so if you look as those x values, we're going to start looking at limits. So if we try to look as, we know as x goes to infinity, the function value is going to go to 2. So if we want that to go to 2, you can look at what happens right after that vertical asymptote. So if we look at the function for like x values at 2, x value of 3, x value of 4, you can plug them in and see what happens, but it's going to be positive. Plus, if you're looking for where the graph lives on this right half, it doesn't have any other x-intercepts, so it has to live in this upper region for the right half of the graph. Okay. As x goes to negative infinity, we also know that the function goes to 2 because of the horizontal asymptote. And we already see in this sort of modified fourth quadrant an x and a y intercept. So the curve is going to live in that region, but you can look as x approaches 1 from the left to see what it does as x tries to get really close to 1. So you can look at values like 0.2, 0.4, 0.7, 0.9, something really close to 1 as it gets closer and closer to 1 on the left. But you'll end up with a positive number up top and a negative number on the bottom, right? 0.2 minus 1, 0.3 minus 1, 0.9 minus 1. The value will be negative on the bottom. So the overall value would be negative, and it's going to point down to negative infinity. And even as the x values get more and more negative, we already see that it approaches 2. So it comes up, crosses this x-intercept, and then tries to approach the horizontal asymptote at 2. All right. So there is a sketch of your graph for